A modern bridge lasts 50 to 80 years. Then the concrete cracks, the steel corrodes, and the whole structure gets demolished. In Quanzhou, China, stone beams weighing 200 tons each have been sitting over open water for 1,000 years. No steel, no concrete, no maintenance. 7 bridges, 3 continents, 3 types of impossibility, and one question that nobody in modern engineering wants to answer. Did we progress toward durability or only toward speed? The Luoyang Bridge in Quanzhou stretches over a tidal estuary where the East China Sea pushes salt water inland twice a day. Completed in 1059 AD during the Song dynasty, it spans 834 meters of open water, longer than most runway strips. And here is the problem every modern engineer will understand immediately. You cannot set foundations in a tidal zone. The current pulls everything away. The salt eats the material. The shifting seabed refuses to hold weight. Today, we solve this with cofferdams, steel pilings, and pumping systems that cost hundreds of millions. The Song dynasty engineers had none of that. What they had was a scheme that no one has been able to fully replicate. They waited for low tide. They sank massive stone blocks, raw granite, uncut, directly into the estuary bed. Hundreds of them. Enough to form a continuous reef of foundation stones across the entire width of the estuary. But they knew the current would shift them. The tidal pull on a loose granite block in an estuary is enormous, enough to slide a boulder the size of a truck. So they did something that makes marine engineers stop and stare. They seeded the gaps between the blocks with oysters. Living oysters. The adhesive budget? 0. The warranty? A millennium. Over years, the oyster colonies grew into the stone, fusing the blocks together with a biological cement stronger than any mortar available in the 11th century. Let that sink in. They used a living organism as a construction material, not decoratively, structurally. The oyster reefs became the foundation, a self-reinforcing biological platform that actually gets stronger as the colony grows. And then, on top of this bio-cemented base, they placed stone beams, some weighing close to 200 tons each, across open tidal water, with a precision that left gaps of less than a centimeter between the beams. To put 200 tons in perspective, that's the weight of roughly 40 African elephants concentrated on a single granite slab lowered onto pillars rising from the sea. With no crane, no hydraulic lift, no powered machinery of any kind. The bridge still stands. Researchers from the Chinese Academy of Sciences measured the structural load capacity in 2004 and confirmed that the beams haven't shifted in nearly a millennium. The oyster cement hasn't cracked. The tidal forces that should have torn the foundations apart were neutralized by the very biology the builders introduced. Here is what that means in practical terms. Modern marine engineers spend billions on anti-corrosion coatings, cathodic protection systems, and constant monitoring to keep bridge foundations intact in saltwater. The Song dynasty solved the same problem with shellfish, and their solution has outlasted every coating we've ever manufactured. But here is the detail that pulls this story somewhere stranger. The Luoyang Bridge isn't unique. Across Fujian province, at least 4 other Song-era bridges use the same oyster-cemented foundations supporting megalithic beams over water. The Anping Bridge, which at over 2 kilometers is one of the longest ancient stone bridges ever recorded. The Shijing Bridge, the Dongluo Bridge. Each one displays the same oyster seeding technique, the same megalithic beam placement, the same absence of mortar. That's not a lucky experiment. That's a coordinated engineering tradition spanning hundreds of kilometers of coastline. And for this tradition, no training manual, no engineering document, no technical school has ever been found. Someone taught these methods. Someone standardized them across an entire province. But the records are completely silent. So the question becomes, if the builders of Quanzhou turned biology into structural engineering, was this the only time the ancient world fused living systems with construction? Stone is one answer, biology is another, and the bridges of Meghalaya prove that the ancients didn't just use nature, they programmed it. Deep in the jungle ravines of northeast India, the air hangs thick with moisture. Waterfalls crash through sandstone gorges 100 meters deep. The monsoon dumps 12 meters of rain per year, more than almost anywhere on Earth. And in this waterlogged chaos, the Khasi and Jaintia peoples grow their bridges. They don't build them, they grow them. The process starts with a Ficus elastica, a rubber fig tree planted on each bank of a river gorge. The aerial roots are trained to cross the gap using hollowed-out betel nut trunks as guides. The root tips reach the opposite bank, take hold in the soil, and begin to thicken. Over 15 to 30 years, the roots intertwine, fuse, and form a walkable structure dense enough to carry human traffic. A living bridge. And here is what separates this from a curiosity. While digging into this, we found that these bridges do not degrade. They get stronger. A conventional steel and concrete bridge loses structural integrity from the day it opens. Wind, load cycles, weather, vibration, every year chips away at it. The rebar corrodes from the inside. Microcracks propagate through the concrete. Within 50 years, most modern bridges need major structural repair or outright replacement. A living root bridge gains mass. New roots grow into the structure every season. The root network thickens. The bridge at Nongriat village, a double-decker, 2 walkable root bridges stacked one above the other, is over 180 years old, carries the weight of 50 people at a time, and the Meghalaya Department of Engineering confirmed in 2016 that its load-bearing capacity is still increasing. A bridge that improves with age, while ours start crumbling on schedule. But the math raises a harder question. If it takes 30 years to grow one bridge, and there are over 70 documented root bridges in Meghalaya alone, many of them in clusters of 3 and 4 spanning the same gorge at different heights, forming layered infrastructure, then someone was planning transportation networks across generations. Not one person's project, not one chief's ambition. A multi-generational engineering program in which a grandparent plants a tree, knowing only a grandchild will cross the bridge. That requires institutional knowledge. It requires codified techniques for selecting the right tree, the right trunk diameter for the guide, the right angle for root training, the right soil chemistry on the receiving bank. And yet, the Khasi have no written language, no blueprints, no construction manuals. Everything was passed mouth to mouth, hand to hand, generation to generation. A biological engineering tradition with 0 documentation and a 100% success rate across 7 decades of modern observation. The real puzzle is not whether this works. The puzzle is how a system this complex survived intact without a single written record when our concrete bridges, built from thousands of pages of specifications, fall apart in 50 years. Stone and biology, 2 answers to an impossible problem. But the Romans had a third: speed. And what they did with it on the Danube is something historians still argue about. because it shouldn't have been possible. 105 AD. The Roman Empire needs to cross the Danube, not with a ferry, not with a pontoon, with a permanent bridge capable of moving an entire army, cavalry, siege engines, supply trains, across a river over a kilometer wide with a current fast enough to drown a horse. Emperor Trajan gives the job to Apollodorus of Damascus, the architect behind the Forum of Trajan in Rome. Apollodorus surveys the crossing point at Drobeta. The river is a nightmare, wide, deep, and fast, with a bed of shifting gravel and clay. No bridge in the empire has ever spanned anything close to this distance. And then he does something that reads like a typographical error in the historical record. He builds the bridge in roughly 1 year. A timber and stone hybrid, over 1,100 meters long, resting on 20 massive stone piers sunk into the riverbed. Each pier, a monolithic block of stone and Roman concrete lowered through moving water and anchored to an unstable bed. The piers alone required underwater construction in a river that kills anyone who loses footing. Modern engineers solve this with pressurized caissons and steel sheet piling. Apollodorus had wood, stone, and human muscle. The evidence points to a technique the Romans used but never fully documented: double-walled cofferdams made of timber, driven into the riverbed and sealed with clay to hold back the current while crews worked inside waist-deep in water. Cassius Dio describes the bridge in his Roman History. Trajan's column in Rome depicts it in stone relief. The pier foundations survived into the 20th century and were excavated by Romanian archaeologists in the 1980s. This discovery is documented in D. Tudor's work with the Romanian Academy. This was real. A kilometer of bridge over a lethal river in 1 year without powered machinery. They gave up. Spectacularly. Not the builders, the next emperor. After Trajan's death, Emperor Hadrian ordered the timber superstructure dismantled. The Romans deliberately destroyed their own masterpiece. The stated reason was strategic, to prevent barbarian armies from crossing the Danube into Roman territory. But the engineers who excavated the surviving pier foundations noted something that the history books gloss over. The piers were designed to support reconstruction. The mortise joints and socket holes suggest the superstructure was meant to be removable and rebuildable. Hadrian didn't destroy the bridge to protect Rome. He destroyed it because anyone who held the piers held the Danube. The bridge wasn't just infrastructure. It was a weapon, a permanent choke point over the empire's most critical frontier, and it was too dangerous to leave standing. One empire destroyed its greatest bridge out of fear. But consider this. Another empire built one so precise it never needed to be touched again. And it stands 49 meters above the valley floor. Southern France, the Gardon River Valley. The Pont du Gard rises 3 tiers of arches into the Provençal sky, 360 meters long, 49 meters high, built in the 1st century AD to carry fresh water from a spring near Uzès to the Roman colony at Nîmes. No mortar holds the structure together, no iron clamps, no reinforcement of any kind. Just limestone blocks cut and fitted with a precision that, when the French National Center for Scientific Research ran a full structural survey, produced a gradient measurement across the entire 50-kilometer aqueduct system of 0.24 millimeters per meter. Hold that number. Across 50 kilometers, the water descends a total of 12.6 meters. That is a slope so shallow that a single sheet of paper on edge is steeper. A modern laser level would struggle to maintain that accuracy over such distance without recalibration. The Romans achieved it with plumb lines, water channels, and sighting poles. And now, the numbers. The Pont du Gard has stood for nearly 2,000 years. 0 structural repairs. The French Ministry of Culture classifies the structure as stable. Independent research has shown that every limestone block, each weighing up to 6 tons, was quarried less than a kilometer away, but the precision of the cuts suggests a standardized production system. Block dimensions repeat within millimeters. The arches distribute weight through a geometry that prevents any single point from bearing disproportionate load. The physics is against anything going wrong. Not a monument, not a decoration, a gravity-driven water delivery machine disguised as architecture. And it still functions. 2,000 years of earthquakes, floods, wars, and neglect. Not one structural failure. We build highway overpasses that crack in 15 years and close lanes for 18 months of repairs. The Romans set the standard for precision, but there is a bridge in Turkey that makes even Rome look young. Izmir, Western Anatolia. The Caravan Bridge crosses the Meles River, where the stream narrows to barely 10 meters. Modest, easy to walk past without a second glance. Measured with modern instruments, it is a simple stone slab bridge, flat beams resting on stone piers, no arches, no ornament, no drama. And it has been carrying traffic continuously for 2,850 years. That date is not an estimate. Archaeological surveys conducted by the Izmir Metropolitan Municipality in coordination with the Turkish Ministry of Culture confirmed construction during the 9th century BC, the Lydian era, before Rome, before classical Greece, before the Parthenon, before the Colosseum, before the aqueducts, before every structure we associate with ancient engineering genius. The bridge has carried ox carts, horse-drawn wagons, Ottoman cavalry, modern automobiles. The same stone beams, the same piers. Geological data confirms that the Meles has flooded dozens of times in nearly 3 millennia, seasonal deluges that reshape the riverbed, shift sediment, undercut banks. The bridge didn't move. It didn't crack. It didn't need a single documented repair. The material, local andesite, a volcanic stone with a hardness and density that far exceeds modern Portland cement, was selected with a precision that suggests someone understood not just construction, but longevity. Someone chose a stone that would still be carrying weight when the civilization that placed it was dust. Now compare. The average lifespan of a reinforced concrete bridge in the United States is 50 years. The Federal Highway Administration classifies over 42,000 bridges in the country as structurally deficient, meaning they require repair or replacement to remain safe. 42,000. Not after 2,850 years, after 50. And the Caravan Bridge still carries cars. No warranty, no maintenance contract, still open for business. Something is wrong with that comparison. Either we overestimate our materials or we underestimate theirs. Either way, the quick calculation, the one that says modern engineering is the peak, stops working the moment you stand on a bridge that was old when Socrates was born. And the Caravan Bridge is not the only ancient structure that refuses to obey the clock. Constantine's Bridge, known locally as the Cendere Bridge, spans the Cendere River Gorge in the Anti-Taurus Mountains of eastern Turkey. Built in the 2nd century A.D. by Roman legions in honor of Emperor Septimius Severus, it is a single-arch stone bridge with a clear span of 34.2 meters, one of the longest surviving single-arch spans from the ancient world. No mortar binds the stones. The arch is constructed from massive cut limestone blocks fitted with a tolerance that the Turkish General Directorate of Highways measured in 2011 at less than 2 millimeters across the entire span. The stratigraphic data is unambiguous. This bridge was engineered to survive not just traffic, but seismic events. And survive it has. Eastern Anatolia sits on one of the most active fault zones on Earth, where the Anatolian, Arabian, and Eurasian tectonic plates collide. The 2023 earthquake sequence alone, centered near Kahramanmaraş, registered 7.8 and 7.7 on the Richter scale. Bridges built in the last 30 years collapsed like cardboard. The Senderi Bridge, 1,800 years old, mortarless, built by soldiers, didn't shift a millimeter. There's a detail people prefer to ignore about this. The Roman engineers who built the Senderi Bridge were not academics working in a research facility. They were legionaries, soldiers on campaign, building in a contested frontier zone on a military timetable. They had no finite element models, no computer stress simulations, no material testing laboratories. They had stone, accumulated experience from centuries of Roman construction, and a tradition, an institutional memory of building things that outlast the empire that built them. The empire fell, the provinces dissolved, the roads crumbled, the aqueducts dried up. But the bridge, a single arch of mortarless stone built by soldiers who would never return, is still standing, still carrying weight, still doing the one thing it was designed to do 18 centuries after the men who built it turned to dust. Wait, that's the pattern. 7 bridges, 3 types of impossibility. Megalithic stone beams over tidal water, fused by biological cement no textbook predicted. Quanzhou. Living root structures engineered across generations without a single written instruction. Meghalaya. A kilometer-long timber bridge over a killing river built in 1 year and deliberately destroyed by its own creators. Trajan. Precision stonework maintaining a gradient of 0.24 millimeters per meter across 50 kilometers. Pont du Gard. A stone slab bridge carrying uninterrupted traffic for 2,850 years. The Caravan Bridge. A mortarless single arch surviving 1,800 years of earthquakes on a triple plate collision zone. Senderi. 7 bridges, 3 continents, 3 completely different technologies: stone, biology, timber. 1 shared trait. Every single one was designed for permanence. Not for a budget cycle, not for a political term, not for a contractor's warranty period. For centuries. For millennia. We do not do this anymore. We build for speed. We build for cost. We design for a 50-year lifespan and call it progress. The data speaks for itself. 42,000 structurally deficient bridges in one country alone. Average replacement cycle, 2 generations. Average cost of a single bridge replacement, $15 to $40 million. Multiply that across a century, and it becomes visible. We didn't choose efficiency. We chose disposability, and we called it engineering. Durability was a choice. These 7 bridges prove that every civilization that built them understood something we have forgotten, that permanence is not a luxury, it is a decision. We stopped making that decision. The question is, when? And why? 7 bridges, 3 types of impossibility: megalithic construction, bioengineering, and precision that outlasts everything we build today. But there's a technology even stranger than stone or biology: sound. Instruments inside the Great Pyramid generate infrasound at 5 to 15 hertz. In Peru, a temple produces the roar of a jaguar through water. And on 3 continents, the same frequency, 110 hertz. Next, the technology that was erased: